Hello everybody. In today's session we see these three-phase induction motors. Now in this chapter the contents are like this. We study about the principle of operation of induction motor, concept and production of rotating magnetic field, and the speed of the magnetic field, what we call it as synchronous speed, rotor speed, slip, frequency of the rotor induced EMF, types and constructional features of the induction motors, slip and its significance, application of squirrel cage and slip ring induction motors, necessity of a starter for the motor, okay, and starting the motors using star delta starters, and there are some illustrative examples at the end of these topics. Now if you see the history of the motor, the induction motor is designed in the year of 1824, okay, it is developed in the year of 1824. So further there are several developments on the induction motor. So in 1879 its first primitive induction motor model will be developed by Walter Bailey. Okay. The first alternating current commutatorless induction motors have been independently invented by Galileo Ferraris in the year of 1885 and Nikola Tesla in the year of 1887. So before this we have all the applications of the motors as DC motors. Now when you have studied these DC motors, we have seen that the principle of a motor is whenever a current carrying conductor is placed in a magnetic field, it experiences a force. Due to this force, the conductors will rotate, or the part of the machine on which these conductors are supported, that will rotate. Therefore it causes a mechanical energy developed from the electrical energy. So all the motors will do this electrical energy to mechanical energy conversion. Okay. So this is the first model. Okay, this is the model of Tesla, first induction motor, which is available in the Tesla museum, which is in Belgrade. So the induction motor is the most common electrical motor used in the industries. Okay, or you can say most common electrical motors in any applications is induction motor. This motor is also called as asynchronous motor because it runs at a speed less than the synchronous speed. Synchronous speed is a constant speed. See, three-phase induction motors are the most common and frequently encountered machines in the industry because they are very simple in designing, they are rugged, low price, easy to maintain, okay, wide range of power ratings. Motors of wide ranges of power ratings are available, right from the fractional horsepower to a motor rating of 10 megawatt, okay, runs easily with a narrow change in the speed from no load to the full load value. You can say the induction motor is mostly a constant speed motor. See, the reduction in the speed from no load to the full load will be very small, okay. That is why the motor can also be called as a constant speed motor. So that is why you can say speed as a variation from no load to full load is very small or narrow. And the speed of the induction motor depends on the frequency of the power source. Okay, it is, of course, we can also run the motor at variable speed. Okay, using that I need to go for a speed control mechanism. So if I want to control the speed of the motor, the requirements is a variable voltage, variable frequency, power electronic drive for optimal speed control of the induction motor. So the construction of the induction motor, if you see, there are two main parts: a stator, stationary, okay, part, what we call it as a stator for the induction motor. The stator consists of a steel frame that supports a hollow cylindrical core. You can see the diagram here. We have a hollow cylindrical core here. Okay, this is called the stator core. Okay, so the inner periphery of the stator core is slotted to receive the windings. So you can see we have a coil placed here. This is a coil, or we can also call it as a stator winding. Okay, it is a part of the winding only. It is not fully wound. Just then you can see here, core consistent from a stacked lamination have a number of evenly spaced slots providing the space for the stator winding. You can see here this orange color winding what you are showing, this is the stator winding. I have, this is a laminated core. The outer periphery of the machine is also called as a yoke. Okay. All machines will need a protective part. So, this yoke will protect the inner part from the atmosphere. So, this is a yoke. And there will be a revolving rotor. It is also made up of punched laminations stacked to create a series of rotor slots providing space for the rotor winding. So, these are the two main parts of the induction motor. Now, in the case of a DC shunt motor, what you have is, there also we have a stator and a rotor. So, in the case of a DC motor, the magnetic field remains stationary, the armature will rotate. So, see, the principle of induction motor and DC motor is same. A current carrying conductor placed in the magnetic field experiences a force. In the case of a DC motor, I have magnetic poles like this, a north pole. Below this I have an armature or a rotor, then I have a south pole. Okay. The magnetic field is directed downwards, north pole to south pole. This is the magnetic field. I am placing a conductor here. Okay. This conductor will carry a current into that, now say board or perpendicular to this conductor, and here I have a conductor which is under the south pole carrying current in the opposite direction. Now, what happens here? The magnetic field directions by the pole will be directed down like this. Okay. So, since the conductor is also carrying a current, that also produces a magnetic field. Okay. The magnetic field produced by the current carrying conductor will be given by right hand rule. So, if I apply this rule, okay, holding the conductor with my right hand such that thumb represents the direction of the current flow, the direction in which the fingers are folded will give us the direction of the magnetic field. So, if you see that the magnetic field is, it will have concentric circle, okay, the lines are concentric about the center of the conductor and the direction is clockwise here. I have the magnetic field produced by the main poles vertically down, and if you see on the right side of the conductor, okay, the two fields are acting in the same direction, therefore, the magnetic field will be strengthened on this side, and as the fields are opposite, these two are, the field is weakened here. So, because the lines of magnetic flux are always under tension, these lines will push the conductor in the direction like this. Therefore, this conductor will experience a force in this direction, and at the same time the conductor what you have under the south pole will also experience a force in an opposite direction compared to the conductor under the north pole. I have the armature supported at the center point. Okay. Here two equal forces separated by a distance acting in the opposite direction will give us a torque. So, that torque is responsible for rotating the rotor or the armature in the case of a DC machine in the counterclockwise direction. To change the direction of rotation, I need to change the direction of the armature currents, okay, or currents in the armature conductors, or maintaining the same current, I can also change the polarity of the poles. Okay. So, this is what we have a shunt motor. In the case of shunt motor, if the magnetic poles are produced by a current, then I can say I will be having a winding here. Okay. The winding what you have on the poles and the winding on the armature, they are connected in parallel to a DC supply. Okay. So, this DC supply is responsible for current in the field winding as well as the current in the armature conductor. I need to send current through the conductors so that these current carrying conductors experience a force. In the case of induction motor, it is not like this. Okay. What we do is we connect the stator to a supply. Okay. We connect a three-phase stator winding, okay, which is symmetrical in all respects, either star connected or delta connected to a three-phase supply of a particular frequency, power frequency. In our country, the power frequency is 50 hertz. So, we will be connecting to a three-phase 50 hertz supply. So that supply will produce a rotating magnetic field in the stator. This rotating magnetic field sweeping past through the rotor conductors will induce a voltage. Now the rotor conductors at the both ends are permanently short circuited. Because of that, the induced voltage in the winding, rotor winding, sets up a current. So the current in the rotor conductors is induced by the magnetic field produced by the stator. Therefore, I call this motor as an induction motor. All the induction motors will have a current induced in the rotor by the magnetic field produced by the stator winding. So there are two types of rotor windings, okay, in the case of a induction motor. Conventional three-phase windings made up of insulated wire, we call it as a wound rotor, similar to the windings on the stator. So the rotor winding and stator winding will have a symmetrical structure there, okay. When in this case, if the stator is wound for certain number of poles, the rotor is also wound for the same number of poles. The second type of rotor what we have is will have rotor conductors as aluminum bars shorted together at the ends of at the two ends by two aluminum rings, forming a squirrel cage shaped circuit. Okay, you can see this is what the squirrel cage shape. So you can see here the assembled rotor. Okay, so this is where you have the bars. So the bars at the both ends are short circuited. Okay, so this is a short circuiting ring, both they are short circuited here, and there will be a small projection outside for the conductor, so that while rotation this will be giving us a fan effect for sucking air into the machine to take away the heats and all. So the disadvantage of this type of construction is I cannot add any resistance external to the rotor circuits. That is what I mentioned here, no external resistance can be added. Okay, and advantage is there is no slip rings and brushes. So because of the brushes there will be some so you can say friction losses that is absent here. Okay, slip rings are not there. So that means length of the rotor will be slightly lesser for the case of squirrel cage construction for the rotor. Okay, so the most disadvantage of this is I cannot add any external resistance to the rotor circuit for improving the performance of the induction motor. We have a wound rotor, okay, a complete set of three-phase winding exactly as the stator are wound on the rotor. That means rotor slots also receives the same type of winding as that of the stator. Now usually these windings are star connected, and the ends of the rotor, okay, and three rotor windings are connected to three slip rings on the rotor shaft. This diagram I can also draw it on the board and show you. Let us say I have this as a stator of the induction motor. Okay, like this we have, this is the stator of the induction motor. Now on the rotor I will have same type of windings also wound. Okay, so now these are the three ends, first end of the first phase, second phase, and end of the third phase. These windings are all connected to three slip rings which are mounted on the same shaft on which the rotor is supported. So these rings are insulated from each other. The first coil will be connected to first ring, second one will be connected to second ring, third one will be connected to the third ring, like this. Through the brushes I can either short circuit them or I can make a provision for connecting an additional resistance. This is also star connected resistance. Equal amount of resistance will be connected in all the three phases, okay, and it will be a variable resistance like this. So now in the case of a squirrel cage rotor, I will have same type of stator structure, but the rotor structure will be a different one. Okay, if this is the rotor, I have a conductor here, another conductor, third, like this. On the periphery, what you have the rotor conductors, and all these conductors are short circuited through end rings like this. Okay, Now here what happens, whatever the magnetic field is produced by the stator, that will be linking with the rotor, an EMF will be produced. Okay. Now this induced EMF, because all the three coils are short circuited through the external resistance, will set up a current. Now because they have windings in the rotor circuit is also symmetrical, all identical windings, same number of turns will be there in each one, same type of conductor cross section is also used, therefore the resistance is also same for the three phases. For all the three phases will have equal amount of current, and they are distributed by 120 degrees between them. Okay. So these are the slip rings. It is also possible to remove this resistance and insert a bar into the rotor slip rings, so that they are permanently short circuited. Okay. That is also possible. Whenever I want to improve the system performance, I can introduce a resistance into the rotor circuit. Through adding a resistance, I can improve certain parameters like starting torque, and I can also control the induction motor speed by placing this resistance. So therefore, the advantage of slip ring motor is, by adding a rotor resistance, I can improve the system motor performance, okay, and I can also control the speed of the induction motor. These are the advantages of wound rotor induction motor. So these advantages are not there in the case of squirrel cage induction motor, as the rotor conductors are permanently short circuited on both the sides. Short circuiting is necessary, whether it is a squirrel cage induction motor or slip ring induction motor, short circuiting is necessary, otherwise there won't be current induced in the rotor circuit. So then I cannot call it as a induction motor. Okay, motor function itself will not be there if these rotor conductors are not short circuited. You can see on the diagram, I can show you three slip rings here. This is the first slip ring, second one, third one. Okay. So this is the rotor, these are the rotor slots which have conductors. So these conductors ends are connected here. So these are the advantages. Okay. Construction is very cheap and it is more robust, slightly higher efficiency and power factor, because I don't have a slip ring and all. Okay. Explosion proof, since absence of slip rings and brushes eliminate risk of sparking. Okay. This is a very major advantage of squirrel cage induction motor. And the advantage of slip ring motor, as I told you, the starting torque is much higher and the starting current also much lower, because it is possible for me to add a resistance into the rotor circuit to improve the starting torque. Okay. Speed can be varied, especially by means of solid state switching. That means I can also use power electronic component to control the speed of the induction motor when the motor rotor is wound rotor. So this is another cut away, or you can also call it as a sectional view, okay, of an induction motor. All the parts are placed here. Okay. You can see, if you from here, this is the bearing. Okay. And then next to the bearing I have three slip rings. You can see here the slip rings. On this I have made a brush arrangement. Okay. We have brush holders and all brushes will be inside. So these brushes will be making contact with the slip ring. Then I have the rotor structure. Okay. This is the rotor. Okay. The other end also there will be a bearing, and this is the extended portion of the shaft what is coming out. This is a terminal box where I will be just taking the three windings of the stator to connect this to a three-phase supply. You can see here, this is what you have, the stator winding on the induction motor. Okay, this is the stator winding. So this is a sectional view. That is why we can see all the inner parts of the machine. It is very difficult to cut the rotor winding. Therefore, it is not possible to, I cannot show any section of the rotor here. So if you see the workings principle of an induction motor, as I told you, this induction motor stator will be connected to a three-phase supply. This stator, whether it is squirrel cage induction motor or slip ring type induction motor, the stator windings are identical. Okay, they are balanced three-phase windings, that is mechanically displaced by 120 degrees from each other, fed by a balanced three-phase source. Okay, so when I am connecting these three windings to a three-phase balance supply, where all the three voltages are equal and the voltages are displaced by 120 degrees apart. Now this voltages will set up three fluxes. In the R phase, the flux value will be phi m sin omega t, this will be taken as reference, and in the second phase, Y phase, I have the same amount of the maximum flux sin omega t minus 120 degrees. Now this 120 degrees difference I will be getting because of the mechanical displacement of the windings by 120 degrees. Okay, between R phase start and Y phase start, there will be 120 degrees. Between Y phase and B phase startings, the phase difference will be 120 degrees. Therefore, I will be getting, if I take this R phase as reference, I will be getting R phase flux as phi m sin omega t and Y phase flux as phi m sin omega t minus 120 degrees, and phi b is phi m sin omega t minus 240 degrees. So the three fluxes what we have, the with RMS value of phi r, phi y and phi b are represented like this. I am taking this phi r as a reference, so phi y will be lagging behind by 120, phi b will be lagging behind by 240 degrees. So all stators, okay, induction motor, whether it is squirrel cage or slip ring, they will have these as the expressions for the three fluxes produced by the stator winding. Now if I see here see, I have a flux of phi r like this, a flux of phi y at the spacing of 120 degrees, this is phi y, and I have a flux of phi b. So this is 120 degrees, is also 120, or the total angle what you have is 240. Now what is the purpose of these fluxes? Okay, see, I don't have any poles here. So if I consider a particular instant when t is equal to 0, omega t is equal to 0, okay, that means for a given position like this, I have the flux phi r will be phi m sin omega t, phi y will be phi m sin omega t minus 120 degrees, and the third flux phi b will have a maximum value of phi m sin omega t minus 240 degrees. At omega t is equal to 0, that is first case, I have phi r is equal to phi m sin 0, so I will be getting this value as 0. Phi y will be phi m sin omega t minus 120, therefore I will get minus 120, okay. So there will be a value for this phi y. Similarly, phi b will be phi m sin of plus 120 or minus 240, there is a value for this, okay. So when you have like this, the value of phi r is 0, phi y will be root 3 upon 2 phi m, okay. This will be minus root 3 upon 2 phi m. So these are all the three vectors. So one has a 0 value, and the second one is root 3 by 2 phi m, and the third one is minus root 3 by 2 phi m. You can see the magnitudes are equal, but they are having a different sign. So phi b, what you have here, phi b will be, phi y is root 3 by 2, okay, phi y will be root 3 by 2. I think this should be negative, the third one will be positive, this is negative, this is positive, okay. So therefore your phi y is here, when it is negative I should take this in the reverse direction because the flux is negative, okay. So the resultant flux will be sum of these two. If I write like this, this is my resultant flux, okay, phi resultant. The value of the resultant will be the vector sum of phi y and phi b. Okay. So, the vector sum of phi y and phi b will give us, see now this total angle what you have between phi r and phi b is 120 degrees. When I extend this in the reverse direction, this angle becomes 60. Okay. So, this is a diagonal, longer diagonal, and the shorter diagonal are like this. They are perpendicular bisectors. Okay. Therefore, this angle becomes 30. Here the longer diagonal bisects the angle 60. Therefore, when I have here root 3 by 2 phi m as the value for this, okay, the total resultant flux what you have, phi resultant will be 2 times root 3 by 2 phi m cos 30. Okay. So, I will be getting here 2 cancels here, cos 30 is root 3 by 2. So, root 3 into 3 will become 3 by 2 phi m. So, this value becomes to be 1.5 phi m. Okay, like this. For the next instant if you see, okay, so this calculation I have already given on the slide, so you can refer that. So, for the next instant when omega t is equal to 60 degrees, okay, when omega t is equal to 60, I just write it here, omega t is equal to 60, your phi r will be phi m sin 60 degrees, which comes to be root 3 by 2 phi m, okay, root 3 by 2 phi m, and phi y it is phi m sin of 60 minus 120. So, this is again phi m into root 3 by 2, but negative, minus, okay, it is negative because I have an angle of a negative angle there. So, because of that the resultant is now, it is because of phi r and phi y. What happens to phi b? I will be getting 60 minus 240, okay, 60 minus 240 will give you 180 degrees. Therefore, I will be getting a 0 degree there, okay, 240 minus 60, I will subtract this. So, I will be getting around 180 degrees. Therefore, sin 180 is 0, therefore, my phi b becomes 0. So, for all these instants when omega t is 0, one of the flux is 0, that is phi r is 0. When omega t is equal to 60 degrees, I am having a phi b becoming now 0, phi r and phi y are there. So, the resultant because of these two will be given by completing the parallelogram like this. Again, this resultant flux is also is equals to 1.5 times phi m. Okay. So, you can see this again 60 degrees. The longer diagonal is perpendicular bisecting the angle. I have this shorter diagonal, these two are perpendicular bisectors. So, this length what you have will be phi r, that is root 3 by 2 phi m into cos 30. Because I want the full length, I write this equation like that. Okay. Again the resultant flux comes to be 1.5 times phi m. You can see here I am taking omega t is equal to, I have taken omega t is equal to 0 at the beginning and I moved to 60 degrees. Now, this omega, it is the angular velocity, okay, with which the supply voltage is moving or rotating in the counterclockwise direction. Now, because the supply voltage is rotating in the counterclockwise direction as the phase sequence of with a phase sequence of r by b, the fluxes also will have the same angular velocity. Therefore, when I moved by 60 degrees in the clockwise or in the counterclockwise direction, my resultant magnetic field, it is moving in the clockwise direction by 60 degrees. So, this is what you have a starting position. I have here 30 and this is also 30. So, 30 plus 30, it is moved by 60 degrees. I will go for the next instant when omega t is equal to 120. Okay. When omega t is equal to 120, I have phi r will be phi m sin 120, okay, sin 120. This is again root 3 upon 2 phi m. Phi y will be phi m sin 120 minus 120. This is becoming 0. Phi b will be phi m sin of 120 minus 240. This is again phi m sin of minus 120. This comes to be minus root 3 by 2 phi m. So, because it is negative, I should write phi b in a reverse direction like this. This is our phi b when omega t is equals to 120 degrees. Now, the resultant is because of phi r and phi b. Therefore, completing the parallelogram again, okay, I have my resultant flux coming to be like this. This is again your phi resultant, which has a value of 1.5 times phi m. Okay. Now, see, I started with 0, moved by 60 degrees, then from 60 by 120 I moved in the counterclockwise direction. Okay. So, now my resultant magnetic field is being rotated in the clockwise direction by the same angle of 120 degrees. Like that, if I go for 360 degree rotation, my resultant magnetic field also rotates by the same angle, but in an opposite direction. Now, you see, for all the three resultant voltages, what I have resultant magnetic fields, what I represented, the magnitude is remaining constant at 1.5 times phi m. Okay. So, I just given another 180 degrees, suppose another 60 degree rotation will cause the resultant flux to be given by these two, phi y and phi b. Okay. With phi b negative, my flux will be like this. Okay. So, this is for 180 degree rotation of these three fluxes in the counterclockwise direction. The resultant magnetic field will be in the clockwise direction. Suppose if I want to change the direction of rotation of the magnetic field, okay, instead of making it rotate in the clockwise, if I want to have it in the counterclockwise, then I need to change the direction of the three fluxes phi r, phi y and phi b. So, I am supposed to make this clockwise, then the rotating magnetic field will move in the counterclockwise direction. So, these are the different, say, instants at which we considered for the calculation of resultant magnetic field in the case of induction motor. So, by this we can say, when the three phase winding of the induction motor, whether it is delta connected or star connected, okay, when it is given a three phase supply, a rotating magnetic field, okay, of constant magnitude, okay, will be set up. The direction of the rotating magnetic field is opposite to that of the direction of the three fluxes, okay, rotation, okay, opposite to the rotation of the three fluxes. Now, to change the direction of rotation of magnetic field, we need to change the direction of rotation of these fluxes. Okay. The direction of rotation of the fluxes depends upon the phase sequence of the supply voltage. If the phase sequence is RYB, I will have the rotation of the magnetic field in one direction. If I change it to RBY, the direction of the rotating magnetic field will change. So, the rotating magnetic field with a constant magnitude is produced. What is the speed of this rotating magnetic field? So, the speed with which the magnetic field rotates, it is called as the synchronous speed, and it is given by an expression ns. S stands for synchronous, okay. It is equals to 120 f divided by p, where f is the supply frequency, p is the number of poles to which the stator winding is wound, okay, and of course ns, I told you, it is called as a synchronous speed. It is measured in revolution per minute. When I take ns in revolution per minute, 120 f by p is the expression for that. Now, see, for a given motor, when it is fed from a given supply frequency is constant, therefore F is constant. When I wound the stator for a definite number of poles, I will not be changing, okay, the number of poles, therefore P is also constant. So in this expression 120 F by P, that is, this expression will give you a speed which always remains constant for a induction motor, therefore I call it as constant it is called as a synchronous speed or a constant speed. Now to vary this, either I need to vary the number of poles or the supply frequency. I have a table here indicating different number of poles for the induction motor and for two different frequencies what normally used in I just gave a table. The comparison is like this: the minimum number of poles to which the stator of the induction motor can be wound is 2. I cannot have a single pole, okay. So when minimum number of poles is 2, 120 F divided by P. If the frequency F is 50 Hertz, 120 into 50 divided by 2 will give you 3000 RPM. This is the maximum speed what is possible for an induction motor in our country. If you go to US or units where the frequency is 60 Hertz, okay, for the same number of poles, because the frequency is more, the synchronous speed is also larger, 3600, okay. Similarly, as the number of poles increases for a given induction motor for a given supply, okay, frequency is 50 Hertz, the synchronous speed keep on decreases. You can see 3000. When I double the poles, it is 1500. When I increase the pole from 3 times, 2 to 6, my speed is 3000 divided by 3, 1000, like that. 8 will be 750, 10 will be 600, 12 poles, 500 is the RPM, okay. Like that, as for the same number of poles, if I increase the supply frequency, I can get higher speed for the rotating magnetic field. See, the principle of operation for the induction motor is like this. I have just shown on the board that when I supply the stator of an induction motor from a 3-phase supply of a given frequency, I will be getting a rotating magnetic field. So this rotating magnetic field sweeps across the rotor windings and produces an induced voltage in the rotor windings. I told you whether the motor is squirrel cage type or slip ring type, the rotor windings are short circuited. So because of this short circuiting the rotor windings, okay, if I am using squirrel cage induction motor, the short circuiting is through end rings, okay, and if it is a slip ring type, I will be using an external resistance in the slip ring circuit to short circuit the rotor windings. So both the cases, the induced voltage induces or sets up a current because of the short circuiting of the windings. So this current will produce its own magnetic field. So the interaction between the two magnetic fields will give us the electrical energy getting converted to mechanical energy, okay. So the current carrying conductors under the rotating magnetic field experience a force. According to Lenz's law, current induced in the rotor conductor should oppose the cause of producing it. So the induced currents are because of the induced voltage, and this voltage is because of the rotating magnetic field. Therefore, according to Lenz's law, the current induced in the rotor conductors should oppose the rotating magnetic field, okay. So the rotor will rotate along the direction of rotating magnetic field in opposing the rotating magnetic field, okay. So therefore, see, when the rotor is stationary, there is no speed for the rotor, okay. So the stator magnetic field what you have rotating at a synchronous speed ns and the rotor speed 0. So if I compare these two speeds, there will be a relative speed between the rotating magnetic field and the stationary rotor. So this relative speed is ns minus 0 when the rotor is stationary, okay. So therefore the relative speed is more. So to oppose the current in the rotor conductors while opposing the rotating magnetic field, causes the rotor to rotate in the same direction as that of the rotating magnetic field. So because of this, the rotor also rotates at a speed. If the rotor speed is equal to n and the stator speed is ns, the relative speed what you have is ns minus n. The minus sign is because of the two are rotating, both are rotating in the same direction. That is why there will be a minus sign. Okay. So now compared to the stationary condition of the rotor, the relative speed is now lesser, ns minus n. At the time of starting, the relative speed is ns. When the rotor starts rotating, I have the relative speed as ns minus n. So the speed of the rotor gradually increases, and while opposing this, the rotor always try to catch the speed of the rotating magnetic field. Okay, but it can never do so, because if the rotor catches up with the speed of the rotating magnetic field, then the rotor also will run at the synchronous speed. So what will be the relative speed between the rotating rotor and rotating magnetic field of the stator? Ns minus n. The relative speed becomes 0. When the relative speed is 0, there won't be any EMF induced in the rotor conductors. When there is no EMF induced in the rotor conductors, no current will be there on the rotor, in the rotor conductors. When the rotor conductors are not carrying any current, there is no production of torque. Okay. So when there is no production of the torque, means the electrical energy what is given to the motor is not getting converted to mechanical power. That means if the rotor tries to run at synchronous speed, I don't have the conversion of electrical power to mechanical power. Okay. That means the function of the motor is not there. Therefore, the rotor will always try to catch up the synchronous speed, but will never do so. Okay. It is not possible for the rotor of the induction motor to run at synchronous speed. It may run at very close, okay, to the synchronous speed, but always there will be a small difference between the speed of the rotating magnetic field and speed of the rotor. Okay. Hence I say, as I told you, the rotor will not be able to catch up with the speed of the magnetic field, okay, but rotates at a speed slightly less than that of synchronous speed. At what speed will the induction motor run? Can the induction motor run at synchronous speed? Why? Okay. The answer I already given to you. If rotor runs at a synchronous speed, which is same as the speed of the rotating magnetic field, then the relative speed is 0 and the rotor will appear stationary to the magnetic field. Therefore, no EMF will be induced, as the conductors are not cutting the magnetic field. Okay. So because of the no EMF induced, no current will be there in the conductors, rotor conductors. So the answer is there. So when the speed falls, the rotor magnetic field will cut the rotor windings and the torque is produced. So to have the electrical input to the motor to get converted to mechanical power, a torque production in the induction motor is a must. If I want to have a torque production, the rotor should always carry a current. This happens only when the rotor magnetic the speed of the rotor is lesser than that of the rotating magnetic field. Okay. So therefore, this is the reason why induction motor always runs at a speed lower than that of synchronous speed. So the difference in the speed what you have between the two speeds, that is speed of the rotating magnetic field and speed of the rotor, I will call it as slip speed. Okay. This is an indication how the rotor of the induction motor is slipping back from reaching the synchronous speed. Okay. So ns is the synchronous speed, n is the speed of the motor. Now, if this speed, slip speed, is expressed as a percentage of synchronous speed, okay, if it is expressed as a percentage of synchronous speed, then I call it as percentage slip, okay. Otherwise I write slip is equal to the ratio of slip speed to the synchronous speed, okay. Ns minus n upon ns will be the slip. It indicates a factor that by how much speed, okay, the rotor is falling back from reaching the synchronism, okay. Synchronism is nothing but the speed at which the motor is running. I told you, the rotor will be always running at a speed lesser than the synchronous speed. So by what percentage of the speed the rotor is falling back from the synchronous speed, that is indicated by the slip. Now here the minimum value of the slip is 0, okay, that is when n is equal to ns, I will having a 0 speed, okay. If the rotor runs at synchronous speed, that is when n is equal to ns, the numerator is 0, therefore slip s is equal to 0. If n is equal to 0, okay, then slip will be equal to ns upon ns, this becomes 1, okay. Slip equals to 1 means the motor is about to start, okay. So at the time of starting the slip will have a value of 1. It is not possible to have the slip as 0. Theoretically I can say the rotor is running at synchronous speed, okay, but practically it is not possible, therefore we cannot have slip equal to 0 in the case of induction motor. It may be smaller, okay, it may be smaller because slip is ratio of two speeds, okay, there is no dimension, no units for the slip. The frequency of the induced voltage in the rotor, okay, I told you when the stator magnetic field which is rotating at a synchronous speed, okay, cuts the rotor conductors, there is a voltage induced. So that induced voltage is proportional to the relative speed, okay. If I consider the starting condition of the motor, at the time of starting, that is rotation of the rotor, I have ns is equals to 120 f divided by p. At starting n is equal to 0, okay, both you can measure in rpm, n is 0 here. So what is the relative speed or slip speed? This is equals to ns minus n, so n is 0, therefore I have ns. Ns is given by 120 f divided by p, number of poles. So now I have a larger amount of, because n is 0, I have a large relative speed, therefore at the time of starting there will be a larger current voltage induced in the stator, therefore the current in the rotor conductors is also larger, okay. Now under running condition, let us say the motor is started, okay, it is running under running condition, speed of the rotor or motor, whatever you write, it is equals to n. Now again the relative speed or the slip speed what you have will be ns minus n. This will be definitely lesser than ns, okay. So because of this the induced voltage will have a lesser magnitude, therefore the current also will have a lesser value in the rotor conductors. Now both the cases I can calculate what is the frequency of the currents in the rotor. Under running standstill condition or when under the starting condition, the frequency of the rotor current, okay, and the frequency of the rotor induced voltage both are proportional to this, okay, Ns. So, as we have Ns is proportional to supply frequency, the induced current in the rotor at the time of starting will have a frequency of f. Under running condition, the induced voltage and the current in the case of rotor will be proportional to slip speed, which I can write it as 120 f dash divided by p. Okay. This slip speed I can write like this. So, if I take frequency of rotor current, okay, under running condition, divided by frequency at starting, I have an expression like this. This is equals to Ns minus N divided by Ns, okay, which I write it as slip, because frequency at the time of starting is proportional to synchronous speed, as the rotor speed is 0. Under running condition, it is proportional to the slip speed Ns minus N. So, we have here S is equals to 120 f dash divided by p, 120 f upon p. So, pp 120 cancels, I have S is equals to f dash upon f, or the frequency under running condition is equals to slip times the frequency under at the time of starting, or supply frequency. Okay. So, today's session we saw about the construction of the induction motor, principle of operation of the induction motor, and the rotation of the production of the rotating magnetic field when the stator of the winding is supplied to a 3-phase supply, connected to a 3-phase supply, okay. And also we defined what is the slip of the induction motor and the frequency of rotor currents in the induction motor. Now, in the next session I will be doing some more simple topics about the induction motor before doing the problems on the induction motor. Thank you.